Where does a rocket experience its greatest aerodynamic loads during launch? At the edge of space? Almost in orbit? Neither. It usually happens about a minute after liftoff. It's called max Q. Calculus explains why.
Passing through max Q is so important that SpaceX calls it out during almost every launch.
Coming up on max Q, maximum aerodynamic pressure.
As a rocket climbs, two things happen. It flies faster, but the atmosphere becomes thinner. Those two changes compete with each other. Higher speed increases aerodynamic pressure. Lower air density decreases it. Max Q is the moment when their combined effect produces the maximum dynamic pressure. This causes the greatest aerodynamic loads on the rocket. Dynamic pressure is given by this equation. It measures how strongly the air pushes against the rocket. Here, rho is air density, and v is the rocket's speed. The rocket must withstand the aerodynamic loads caused by this pressure. That is why many rockets throttle down just before max Q. Once they pass it, they throttle back up. Both air density and speed change with altitude. Air density decreases, speed increases, so dynamic pressure also changes with altitude. It is a function of altitude z. Now here's the question. How do we find the highest value of this function? This is exactly what derivatives are for. A derivative tells us how a function changes. When the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. At a maximum point, the function changes from increasing to decreasing. So at that point, the derivative is 0. dq over dz equals 0. Now let's build a simple model. As a first approximation, suppose air density decreases exponentially with altitude. Here, h is the scale height. The altitude over which air density falls to about 37% of its sea level value. On Earth, it's about 8 kilometers. Now suppose the rocket's speed increases approximately in proportion to altitude. This model is not exact, but it captures the essential competition between increasing speed and decreasing air density. Now substitute both expressions into the aerodynamic pressure equation. Now let's differentiate. Setting the derivative equal to 0, we get two solutions, z equals 0 or z equals 2h. The first solution is simply the launch point, so our model predicts that max Q occurs at an altitude of 2h. Since h is about 8 kilometers, the model predicts max Q at an altitude of about 16 kilometers. Now let's compare that with reality. Falcon 9 typically passes through max Q at an altitude of about 12 to 15 kilometers. The Space Shuttle passed through max Q at about 11 kilometers. Saturn V passed through max Q at about 13 to 14 kilometers. So even this simple model predicts the correct general range. Of course, real rockets are much more complicated. Air density doesn't follow a perfect exponential. Rocket acceleration isn't constant. Engines throttle down. Fuel burns off. Wind also plays a role. These effects change the exact altitude of max Q from one launch to another. That is why engineers use detailed numerical simulations. Max Q occurs when the combined effect of speed and air density reaches its maximum. And calculus allows us to find that point. Please like, comment, and subscribe. It really helps the channel take off. Thank you for watching.